All right, guys. So if I'm not mistaken, we finished at the moment where we were trying to calculate square roots, correct? And how would you go about doing that? I am sure that many of you. Oh, here we go. That's good. Oh, 1 second. Some people still join. Give me a small second, guys. I'm sure many of you have watched that video by Veritasium that I sent you about Newton's formula of how to, and that's a very nice formula for not only calculating the square roots, but also for approximating the digits of pi. And it comes from the binomial theorem, which we do cover in the other class. And it obviously is related to calculus, guys. So imagine you have no calculator and you have to figure out what is the square root of 2. How might you have proceeded? How might you proceed? It's very interesting is that what you can do something rather trivial, guys. Look at it. I take root of 2 and I write 1 plus root 2 minus 1. Doesn't seem like I have accomplished anything, right? I mean, I just wrote a tautology, triviality. Now let's continue, and this looks like a minus b. Maybe if I multiply by a plus b, I complete the square. Do you see what happens, guys? Do you see this step? So this is 1 plus, I multiply that by square root of 2 plus 1, obtaining 2 minus 1 or 1 divided by root 2 plus 1. Am I right? Well, hopefully I am.
Professor, could you please repeat what you did again?
Of course, I simply multiplied root of 2 minus 1. You can see it on the denominator. I multiplied this thing in parentheses by root 2 plus 1. And if I multiply by root 2 plus 1, I divide by same thing. And yes, Grant, you can call it multiplication by conjugate, correct? What do we get here? Now let's look at this thing. We have this piece, which is this piece. So what do we have here? Now this piece, guys, I can make look like what I have in this box. Look how interesting. This is 1 plus 1, and on the bottom here I see 2 plus root 2 minus 1. Do you see that? And now observe that what I have here in this red box is the same thing that I have over here. Do you see this? Same thing. Which means that I can take this in this process. I can just replace this small red box by this full thing. Look at it. This red box is this full thing. It means this is that this is 1 plus 1 over 2 plus 1 over 2 plus and onwards. Do you see what I just arrived at? Are you with me, guys? 1 over 2 plus 1 over 2, right? So it's very simple. You see, all I do is I just take this red box, and this red box is this whole expression. So I can replace this box by this whole expression. And I continue doing that many times, and I get this formula. Now you might think, okay, what does it do to me? I mean, I just do it forever. Does it help me with anything? Now let's look at what we observe here. Let's observe what we are getting here. 1 second, one more person joined. Let's hope that we will not lose that person as well. One moment. All right, let's get going. You see that, guys? I have 1 plus 1 over 2 plus 1 over 2 plus 1 over 2. Amazing, beautiful. And what it allows us to do is this approximation. Look at it. I have approximation number 1. I just begin by saying 1 plus 1/2. If I may, maybe I should mention, just to gather myself, this tells me that I can get, if I just look at this part, so I just, this part, I have this sequence, I have the sequence an. All I have to do is an is simply 1 over 2 plus plus an minus 1. Just take 1 over 2 plus the previous term, and that will eat it up. You see how I know that? Because look at it. This is my, if you think of this red part, if you think of this red part as an, then this is 1 over 2 plus an minus 1. I create a recursion for any root. It would work for root 5. And I will show you afterwards another calculation in case you decided to watch that binomial formula. That other formula, you can obtain it by taking multiple derivatives, by asking whether a root is a polynomial, just like we did for e to the x. You can obtain Newton's approximation. Good? So those ideas are very, very powerful. So what does it mean? Look at it. Just this idea, if you thought a little bit about it and kind of pushed this forever to infinity, this process, you would have obtained an approximation of root of 2. So I can say, okay, first approximation is 1 plus 1/2. Second, I just decided to begin with 1/2, right? Second approximation is 1 plus 1 over 2 plus 1/2. And what is that? Just look at it. This is just a good practice, guys, for you to do if you want to review algebra. I just multiply denominator and numerator by 2, and that becomes 1 plus what? 1 plus 2 divided by 4 plus 1, or so it's 2 divided by 5. You all see how I simplified this fraction into 2 over 5? I multiply denominator by 2 and numerator by 2. So it's 2 over 4 plus 1, or 2 over 5. That's a second approximation. Now let's do third approximation. That would be 1 plus, you see 2 over 5, I just take 1 over 2 plus 2 over 5. And what do we get? We get 1 plus, multiply this by 5, and that would be 5, 10 plus 2, or 12, 5 over 12. Make sure that I do the algebra correctly, guys. All right, arithmetic is good. You're keeping track, yes? Dauda, you see what I'm doing. You keep track, right? I'm not making a mistake, I hope. 3, 4.
Good.
Huh? Looks good, right?
Yeah.
Thank you. I appreciate it. That's 1, 2, 3, 4. What do I do next, guys? Anybody will tell me what's my next approximation? Let's approximate it to 4. What do I do? 1 plus what? According to this process, if you understood how this process was obtained, we do what? 2, 1, yes, also, so it's hard to write, it's a bit unpleasant, so it's 1 plus 1 over 2 plus 5 over 12, which is the same as 1 plus, I can multiply the entire thing by 12, so it will be 12 divided by 12 times 2, which is 24. 24 plus 5 is 29, correct? Guys, I'm terrible at arithmetic, so when I say correct, I'm not just testing you, I'm just being sure that
Yes, correct, 29,
I'm not making a mistake. Good, right? It's arithmetic is my weakness, right? So 5, let's do 5, maybe let's do 5, 6, maybe, or 7. We'll see how many you will do, right? So then, yes, so the next is 1 plus, look what we have here. And then we write 1 over 2 plus 12 over 29, which becomes what? Which becomes 1 plus, I multiply by 29, so it's 29 here. 2 times 29 it's 52, correct? 2 times 50, so it's 52 plus 12, it's 70.
So 29 times 2 is 58.
58, sorry, what did I say? Good, good that I have you to check me. All right, so then 29 times 2 is 58, I think, and then plus 12 is
70.
70, yes, thank you, 70. Good, wonderful, right? It's 29 over 70. Now we can stop maybe at this point and just let's see what's the approximation. You see, if you press it in the calculator, right? Press this. We just did this procedure only 5 times, right? 1 plus 29 over 70 is our approximation currently to root of 2. What's that approximation compared to the calculator? Let's see. So this would be 1 point what? So 29 over 70. The calculator gives what value?
Let's give 0, 4, 1, 4.
Over 70, 0, 4, 1, 4, right? So let's say it's 1.414 285
7, 1.
right? And blah blah blah, right? Now if I press root of 2, let's see how many digits we have gotten. So if I press root of 2 according to the calculator, root of 2 according to calculator is 1.4142 1 3 and whatnot. Look at it, we have 1.4142 and we have here 1.4142. You see, doing this process only 5 times, we have obtained quite a lot of digits. Do you agree? Isn't it interesting how many we attained? A lot of digits. Now would you like to try to find for me root of 5 the same way? I'm sure you would. And so here is root of 5, which I would like you to see if you can figure out. Look at it, just using a basic conjugation method, can you find the full expression, the continued fraction expression for root of 5, and then we'll see if you can find what root of 5 is using very low technology. Okay, we have Moshe. So that thing that you obtained, Moshe, is what? How did you obtain it? I want a continued fraction expression. Yes, exactly. You just put it in the calculator. The point is to figure out how the calculator or what procedures exist to calculate root of 5. No, I know it's fine. I like that you are, but you see why I'm making you do that, guys. Or I'm not sure if you see that. So first, the calculator approximation. All right, let's do it together as we are short on time. So suggestions, what do I do with root of 5? Okay, good. So one person has it. Suggestion, what do I do with root 5? All right. Add and subtract 2, very good. We can do better because we can want a fraction. So root 5, we find what's the biggest integer that's closest to root 5. We know 2. 2 squared is 4, 3 squared is too much. So we take 2 plus root 5 minus 2. We can do that like this, you see? Because root 5 minus 2 will be a fraction. Now we simply take the conjugate. So that's just of this part. 2, what is this part? It's going to be 5 minus 4, which will make it 1. What's the bottom? It's root 5 plus 2. And now you see that root 5 minus 2 and root 5 plus 2 are rather similar. So what do we do next? We write 2 plus 1 over, here I will move 4. 4 plus root 5 minus 2. I don't change the expression. 4 minus 2 is just plus 2. Do you see why I do that? Why do I do root 5 minus 2 here? It's because, look at it, guys. I now have a recursion. This is the same as this. And this box is the same as this full thing. You see? Now this box is the same as this thing. So now I have this this process is that I replace this red box by 1 over 4 plus this expression, which I also replace by 1 plus 4 over that expression. How did I get 4 in the denominator? Look at it. Do you see root 5 plus 2? Root 5 plus 2. Everybody sees up to the point of root 5 plus 2, guys. You have to understand that it's not, you should not think just in terms of process. You just what is that you're thinking is what am I looking for? I am looking for, it's called fractal. I'm looking for the same object within itself. Okay, so here I have root 5 minus 2. Here I have root 5 plus 2. If I remove the 4, I will see 4 plus the same thing. 4 plus the original thing I started with. You understand? Which means that now I have repetition. It now goes again the same way. Do you see that? If I remove the 4, look at it. 4 minus 2 is the plus 2. Do you see that the denominator is exactly the same as the denominator here? You agree? 4 plus root 5 minus 2 is the same as root 5 plus 2. So I haven't changed anything. But by removing the 4, the thing that is in this red box is the same as root 5 minus 2 that I had originally. Yes? And so what we now have is simply 2 plus 1 over 4 plus 1 over 4 plus 1 over 4, like this. Good? Now, what is that? Does it mean? Look at it, guys. It means that that if this is, so I have this recursion. I have that I have that a sub n. Look at it. This part is like the a sub n. It's equal to this part. So a sub n is equal to 1 over 4 plus a sub n minus 1. So I have all I have to do is I have to begin with an initial value, and then take that initial value, add 4 to it, and take the reciprocal. That's what this means. You see, I can use that to generate root 5. You see here, how am I going to generate root 5? Well, so I have first procedure. I can take any number to begin with. I mean, any number smaller than 1 would actually work. The reason for it is that when you look at the situation, it's a sort of quadratic that you get there. But I can pick, if you prefer, I can pick, for example, 1/4. Okay, I'll pick 1/4. Since it looks at 1 plus 1/4. So I have 1 plus 1/4 is my first approximation. Second approximation is 1 plus 1 over 4 plus 1/4. That's my second approximation, which second approximation is 1 plus, let's say, what can I do here? It's 4 over 16 plus 1, so it would be, so it's you say just multiply this and that by 4, so that's 4 over 17. Yes, then 3, that's not 1, that should be 2. I'm sorry, right? 2. We had a 2 there, right? So then it's 2 plus, here I have 1 over 4 plus 4 over 17. And what do I get? So if I have this, it's just simply 2 plus 17 over 17 times 4 plus 4, and so on. Good, and that will give us the digits. So another thing that you can do, you can try this process. Another thing that you can do is as follows, guys, right? So there is this formula, if you watch that, that's maybe the way your calculator can figure it out. So for instance, you have this formula, root of 1 plus x. That's the same thing as 1 plus x to the power of 1/2, which is Newton's binomial formula, which you can establish by asking whether or not it's a polynomial, right? If this is a function f of x, do you remember this, guys? Then it's easy to evaluate at 0, right? Root of 1 is easy, right? So it's easy to evaluate f of 0. It's easy to evaluate f prime of 0. It's easy to evaluate f double prime of 0. the same way we did with e to the x, right? So if I believe that this thing is a polynomial, guys, if I believe that 1 plus x to the power of 1/2 is a polynomial, the polynomial will have, it would be infinite polynomial with coefficients a0, a1 x, a2 x squared plus a3x cubed, and so on. And you will find, if you do the process, it was not unique to E, you will find that the coefficient a sub n is equal to the nth derivative of this function evaluated at 0 divided by n factorial. Okay, which means that the expression 1 plus x to the power of 1/2, 1 plus x to the power of 1/2 will be the same as 1 plus 1/2 x plus 1/2 times minus 1/2 divided by 2x squared plus 1/2 minus 1/2 minus 3/2 divided by 6x cubed, and so on. This is the infinite polynomial that you would obtain if you actually try to do it this way, and the result is pretty interesting. And the result is pretty interesting is that, look at it. If I want to calculate, for instance, root 2, I can think of root 2 as root of 4 minus 2, for instance. You agree? Which allows me to factor out the 4. So it's the same as root of 4, 1 minus 2 over 4, which is minus 1/2. Which allows me to write it as 2 root of 1 minus 1/2. Which according to Newton's binomial formula, it will be 2 multiplied by 1 plus 1/2 multiplied by x is in this case minus 1/2 to the power 1 plus 1/2 minus 1/2 times minus 1/2 squared. It's the x. This is my x. Minus 1/2 squared is x, right? Divided by 2 plus 1/2 minus 1/2 minus 3/2 minus 1/2 cubed divided by 6, and so on. This convergence is very rapid. It's a very fast convergence, and you will get your digits this way as well. Isn't it amazing, guys, right? So what your calculator is able to do, or other machines, they're able to add and multiply very rapidly. And this process just involves addition and multiplication. You create a process that actually is able to digest the input. It makes it very explicit. Isn't it amazing? And that is through the help of calculus, right? So those calculations are calculus calculations, obviously. Calculus ideas. I hope you're impressed, because you see all those approximations are tremendously necessary, right? For the things that you are using. They simplify your life very much, because all of electronics, all of waves, all of things that we are using, they are built on this ability to use simple processes to build a complicated operation. All right, and then we are now ready to move to trigonometry, guys. Let's see how good you remember your trig, the trigonometric functions. Here we are. So trigonometric functions will be measured in radians, guys. Do you remember what are radians and why they are very natural? You do, right? So radian is very natural as opposed to degrees. Why? What is, first of all, a degree? Give me a very, very simple explanation of degree. Very trivial, very down to earth, please. And give me a very simple explanation of radians. Very trivial, very down to earth, please. So measure of an angle is already, yes, you're right, they measure angle, but it's a bit confusing. You agree, guys? Angle, okay? Something that makes me really understand what's degrees and what's radians right away. Yes, 360 degrees is arbitrary, but specifically, what are those degrees, guys? You see, I might be doing this, guys. Right? You can say that I am turning my hands clockwise and then counterclockwise and giving me a very technical description. But you could also say that I'm doing what? Right? All of you, I'm assuming, understand what I'm doing. Right? You all imagine something very, very simple that I'm doing, right? And you're not going to tell me, well, I am rotating my arms counterclockwise and clockwise, and I'm making sounds, right? That means that you don't compress this information into a concept. Yes, turning a steering wheel. Here you go, right, guys? That's what I mean when you imagine. Wonderful, right? You understand that I'm turning a steering wheel. So if I ask you what are degrees, right? Where can I get a degree? What do? You're going to take a pizza and you are going to cut it into 360 equivalent wedges, equivalent slices, right? So a degree is just a Babylonian slice. Easy to remember, yes? And if a degree is a Babylonian slice, then what is radian? The crust. I mean, everybody sees it, right? One person responds crust, but the rest I just did not type fast. I mean, I'm a slow typer, correct? It's the crust. But one more thing about the crust, guys. How do I measure the crust, right? So why is it so interesting to measure the crust? The crust is intrinsic to the circle, right? I don't have to cut the pizza into 360 parts, but the length of the crust is what compared to the radius? And when I say natural, guys, you see the length of the crust, it's a property that the length of the crust is specifically, when you say 2 pi r, you're converting, guys. You see, the length of the crust is 2 pi times the length of a radius. Do you understand? It means roughly 6.28 times the radius. If you have to make it, but it's not a rational number. It's not something that you can report precisely, but the idea is that it's roughly 6.28 times the radius. You understand? And when you multiply by r, it's simply because you measure the radius in terms of inches or centimeters, and then you describe the circumference in terms of inches and centimeters. You see, when you say the circumference is 2 pi r, all you're saying is that if you measure the radius to be 5 inches, then the circumference is 2 pi multiplied by the length of one radius, right? By the length of 5 inches. It's just conversion. You understand, guys? Conversion, in other words, to try to explain it to people that prefer a different measurement. That's very important for you to understand it and to see it. That means geometrically, there is the circle can also always be thought as a unit circle, because 1 means 1 radius. Make the circle larger, the property is still true. You understand? The angle is not dependent on the sides of the pizza. The angle is a proportion of the crust to the radius of the pizza. So if you make the radius longer, the crust becomes longer, but the proportion stays. We're clear. Now, what you can do is you can create those trigonometric functions, guys. And what they are, first of all, the crust, guys, here it is, you see? The angle is, some of you draw it over here like a small circle, but really the angle is right over here, right? It's on the crust of the pizza. So the angle, you draw it counterclockwise. Bigger and counterclockwise means that you're moving the radius counterclockwise. If you have negative angle, you move the radius clockwise. You can imagine that this is a movable crane. I actually think of it as a crane that you rotate. Good. And then I have this right triangle, and I consider proportions of that right triangle. So, for instance, this red rope, this red piece of rope, it is signed. It is signed when I measure the length in terms of radius units. Do you understand? So this length of the red rope compared to the radius is what I consider to be sine. The green shadow here is cosine. Are we clear? This is cosine, this is sine, and now let's see how well can you visualize. Tell me, guys, please, what is sine of 0? What you do is with sine, in other words, you open up the crane to the angle theta in radians, and then you measure the perpendicular rope to the x-axis in terms of radius. Okay, so sine of 0 is 0. You agree? Because if the crane lies on the ground, on the x-axis, the length of the rope is 0. Good. Now, could you please tell me what is cosine of 0? Cosine of 0, it is, okay, I see you're doing it faster than in the morning. That's good. So that is 1. Do you understand why is it 1, guys? Because the green shadow is as long as the crane. Right? Why is sine is 0 and cosine is 1? Now, could you please tell me what will happen if I begin increasing this angle towards a quarter of the circle? So I'm increasing it, increasing it, increasing it. What happens to sine qualitatively? Sine will do what? Right? I turn and turn and turn. What is sine going to do? Goes to 1, increase to 1 to be. That's the best way to say that, right? Sine increases to 1. Right? In the morning, people say, what do you mean? Some people say, what do I mean, right? And of course, I was very mean. I really did mean, and I was very mean. But with us, of course, we understand, right, guys? So this thing is, the radius is turning counterclockwise. What's happening to sine? The rope is longer and longer and longer until at pi over 2. Pi over 2 is 1/4 of the circle. Do you see why? Because 2 pi is the full circle. 2 pi divided by 4, and you get 1/4. Pi over 2. Yes? So, yes, I mean that I mean precisely. Yes, so that's exactly what I meant. So, sine approaches 1, and at pi over 2, it's equal to 1. Do you agree? And what is cosine at pi over 2? Of course, it is 0. Good. You see that it's 0. Cosine is 0. What happens to cosine, my friends, when the angle approaches pi over 2? Cosine goes to goes to 0. Good? Wonderful. We all see that, guys? So we see that sine will increase in the first quadrant, cosine will decrease to 0 in the first quadrant. We'll go from 1 to 0. And you can see that graphically. Just draw triangles here. So some people, here is a triangle. You can see that the red part grew and the green part shrunk. So you can see that, you can imagine it, I suppose. Good. Now, what happens as I move towards the second quadrant? In the second quadrant, you also have to tell me, is sine positive or negative? So sine, this thing, is sine positive or negative? Sine. You see this thing, guys? This rope is measured against the positive y-axis, which makes it positive. Right? We track whether the crane, and if you, of course, know the Russian cartoon Nu Pogodi, you will understand that I think of trigonometry as construction, as something constructible. You will see it in a moment. I'll show you the animation that I created. Yeah. Good. So this is, sine is positive. What about cosine, my friends? Is cosine positive or negative in the second quadrant? Negative. Do you see why it's negative? Because cosine, the green segment, is over the negative x-axis. Yes, Elazar? Yes, Sarah? You see that it's over the negative x-axis. That's why cosine will be negative there. Beautiful, right? So Beautiful, good. So now sine will decrease towards what? What is sine of pi? Sine of pi, guys, is what? Pi means we rotated 2/4, exactly. Sine of pi is 0. What is cosine of pi? -1. If I lie flat on the negative x-axis, then the green shadow is as long as my crane. Good. So cosine is negative in the second quadrant. It's very, you don't need to remember anything. You see second quadrant and third quadrant, that's where the shadow of the radius will fall on the negative x-axis. So second and third quadrant, cosine is negative, whereas sine is negative in third and fourth quadrant, because that's where the red rope is over the negative y-axis. Right? It's very easy. There is no need to remember anything. You understand how the quadrants are developed. You just rotate to them counterclockwise. The angle is negative if you move clockwise. Now, there was a person or two that asked me, how do I know what is this angle in radians, guys? If I want to go to here, that angle in radians is what? In radians, I hate degrees. We do not like degrees here. It's blasphemous to mention them. Yes, well, or if you go Grant, well, you went clockwise, but we can go there counterclockwise. You prefer, it's not the number you want to go. It's -pi/4 if you go this way, this location. It's not the same angle, but if you go this way, the answer is -pi/2. If you go that way, the answer is 3pi/2. And some people ask me, how do I know? Well, it's 1, 2, 3 quarters. So it means I go 3 motions of pi/2, of quarter. Pi/2 is a quarter motion. Good? We all understand. Yes, guys? So we understood cosine and sine, at least qualitatively. We know that sine and cosine range between which and values. So sine, what value can sine never exceed? Sine cannot be bigger than what value? It cannot be bigger than 1. Do you see why? Because the rope, the red rope, can never be longer than the crane. And sine cannot be smaller than -1 because the red rope, again, can be negative, but cannot be bigger. Of course, I'm lying to you guys. If you go to complex analysis, sine can be any value whatsoever. The solution sine of z equal to 20, it's perfectly valid, but then you have to use complex numbers. Yes, that's pretty cool, yes? So it is only true to the extent that we're using real numbers. So much excitement. And of course, how do you understand what is sine and cosine in general? For that, you need to understand how the operation is processing the angle. We don't understand that yet. We just qualitatively see what's happening, right? We don't have a formula that translates the angle by multiplication and addition into a value that we recognize. So in your calculator, when you press sine of pi/7, what is the calculator doing? Right? You understand what is sine of pi/2, but that's only visually, because you see sine of pi/2 it must be 1 because the red rope is as long as the crane. Good? So let's now view our first animation. I think was it is okay, not here. All right, so here we go. Do you recognize the music? All right, so quickly, what's happening here, guys? Let's make it smaller screen. So here you can see theta is equal to 0.3. Where do I see that theta, guys? What is 0.3? 0.3, what is that? 0.3. 0.3 angles in radians. And Elazar, I think you are just seeing, yes, it's 0. You're probably doing a psychological experiment on me. So it is 0.3 of a radian. Do you see that, guys? And sine is very similar because look at it. The degrees, this red line segment and the arc here on the circle are very close to the same size. Here, the difference becomes a bit larger. Here, theta is about this angle. If I opened up this arc here would be about 82% of the radius, and sine, this length here, is about 73% of the radius, you see? And the later picture I will show you still in more, I will show you with another animation that the way the graph of sine can be easily obtained. Let's see that here. Yes, let's see this one. Are you ready? This is showing you how to draw sine. So quickly, now that you listened to the full presentation, do you see what's happening here, guys? Let me pause for this moment. So how is this graph generated? Do you see that this dotted line, it's just the unfolded arc of the circle? Do you see that here we have up to 6 units, because a bit more than 6 units, it's my full pi, right? So, and then you can see that this red segment, I just place it perpendicular to that unfolded arc. And if I do that at every point, I will generate the graph of sine. And you can see that at this moment, the angle theta is 1.95, which means it's almost, this arc is almost, as you can see over here, almost 2 radius lengths. It's almost the same size as the diameter. and sine for that particular value is about 93% of the radius. Clear? Now, notice that this has only 33,000 views. Now, tell me why. That's an interesting quiz question. Does this, no, not this. Why does this video have 154,000 views? Well, yes, because one was Chopin, exactly, and people have very bad taste in music. Precisely. Chopin, right? I am working, as they say, ehrenamtlich, voluntarily, right? Just expending my energy into the air. So yeah, I don't. So yes, this is a video I made. Hopefully you can watch, and it might help you understand sine and cosine. That's and how do you do that? What did I use to make animation? I used my mind. I saw the animation, right? And I saw the mathematics of the animation. You see, guys, I will show you some other funny things there, right? That you can do with sine and cosine later on, right? And then it plays in your mind, and you write a formula for it, and the computer just plays what you have in your mind. I just record it. And you can do that using many things. Like, yes, I did use my brother, it's true. My brother selected the music. My brother, selected both musics. Right? That's not my selection. Right? I would have not selected Chopin for sine. I don't see it fitting. It's a sort of blue collar function. All right. Good. So back to this topic. I use Mathematica. Yes, well, Grant, Grant, if you ever visit Grant, he will torture you about sine waves and cosine waves. He really loves those things. Just, yes, be careful. Right, he's a very good musician, actually. So, yes, he should know. All right, guys, so then what did we observe? We know when sine and cosine and all those things are positive, negative, and we understand their values at certain numbers, right? We understand the value of sine and cosine at the quartiles, at those junctures, right? At quartiles. We know sine and cosine here, 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 and here. Good. Now, my question, guys, where is tangent, right? We have here is we consider ratios of, there are 6 possible ratios, right? When you consider a triangle, right? Triangle, we can think we take the opposite to hypotenuse, or opposite to adjacent, or adjacent to hypotenuse, and all those combinations. You can see there are 6 possibilities. Yes, 6 possibilities. Hypotenuse to adjacent, that's secant. Hypotenuse to opposite is cosecant. Among those, the most important ones, I think, are sine, cosine, tangent, and maybe secant. Okay, so of course those functions are very related, all of them. Sine and cosine are very similar functions. Tangent and cotangent are very similar functions, essentially identical functions with slightly shifted domains. So where do you see in this picture tangent? Where is tangent in this picture, guys? Oh, it is here. Now the question is, do we understand why this is tangent? Tangent is defined as opposite over adjacent, as sine over cosine. Do you agree? Now, tell me, please, just to understand how I make this picture, guys, what number do you prefer to divide by? What's your favorite number to divide by? 1. Isn't it nice to divide by 1, guys? If you understand that you prefer to divide by 1, then why not do that? So, for instance, if I open up the angle theta, you see that I can draw a perpendicular to the x-axis at any point. If it's the same angle, the triangles that will be produced are similar. Do you agree? That, for instance, if I draw the triangle in here, if I draw this triangle, then the ratio of this to that will be tangent of theta, of the same angle. Do you agree? I hope you understand similarity, guys. You see what similarity means is that proportion. I'm saying the opposite to the adjacent of the small triangle, because it has the same angles here, is the same as any bigger ratio of bigger triangles or smaller triangles. Scale remains the same. Do you agree? And so what do? I decide to take the perpendicular right over here. So this segment is of size 1. So Grant, you have to explain to me what's the question. Why were these ratios chosen to be sine, cosine, or tangent? What's the name? Why they were called this? I have no idea, right? I mean, that might be historically interesting, but I have no idea why they were called the way they were called. Okay, and opposite of what not is just what you do is you report on the structure of the triangle, and that's important, guys. If you want to, you can watch. You can see that there is a project. They're constructing a castle, for instance, in France, using old techniques. Okay, using medieval techniques. And they have been doing that for the past 25 years. It's pretty interesting. And you can see at least glimpses of the people, the masons, you know, the people that are dealing with the stones, that are dealing with the structure. They use geometry, they use mathematics, naturally they use trigonometry to decide on such things as the size of the stair, on the relative position of stairs, on the integrity of the structure. So trigonometry was useful in constructing buildings and also in destroying them. Let's say when you consider warfare, when you consider the Turks coming to the city of Constantinople and shooting with their huge cannons against those walls, they were using trigonometry. Okay, so it has very engineering, very, if you're excited about war, right, then, or excited about construction, those things that they were historically related to tangent, and engineers, military engineers have to, of course, understand such things. So why the names, I do not know. Yes. Why the names? That's just names. I mean, why is a person named a particular way? Why is Grant named Grant? There might be, of course, a good reason for that, but if you go ultimately, you don't see any reason. Ultimately, at some point, there is a name, right? So people are named Alexander because Alexander of Great, I presume. But why was Alexander named Alexander? That's, you see, at some point, the name is meaningless. Elazar, what did you send me? Send afterwards in email. You know it. You have you been there? Okay, cool. But you can see some glimpses of how they use trigonometry and those things, right? So here, sorry guys, back to this topic. Yes, they have a series of those videos, and you can see on different aspects of medieval life. I was particularly interested in trigonometry, naturally, right? As you are as well. So this is, guys, this is 1. This is 1. And so opposite divided by 1 is easiest. Look at it. And if this is the triangle, just extend this radius, and you see that this is now your tangent. You see this line? That's your tangent. I hope you see it clearly. Maybe I didn't play it with my other students. Maybe afterwards you will tell me where in this picture do you see cotangent or secant or things that I haven't drawn. Good. Now let's try to understand what happens to tangent geometrically or otherwise if I increase the angle. So what is, first of all, tangent of 0? Type in the comments. Can you visualize tangent of 0 radians? Wonderful. But come on, guys, fast. Tangent of 0. It means what? It means that the angle is 0, opposite is 0, adjacent is 1, right? It's simply here. Now, what happens to tangent as I increase the angle towards pi over 2? What happens to tangent? That's my question. What's limit as theta goes to pi over 2 from the minus? Minus because this is pi over 2 less and this is pi over 2 more of tangent theta. What will I get, please? What will I get if I push theta to pi over 2 minus of tangent? Well, tangent of pi over 2 is not defined, but what do I get as I move taller to that point? As I begin to lift my crane, what am I getting? Increases without bound. Precisely. It's increasing without bound. It increases to infinity. Do you see that, guys, arithmetically? Arithmetically, what happens is that the green curve, look at it. I'm just going to erase it. Yes, it increases to infinity, because look at it, guys. What happens here is a slightly bigger segment, I mean slightly bigger angle. What happens is that the green is getting shorter and the red is getting longer. You see that? The green, if I kind of select a bigger angle, then the red increases, and the red increases towards 1, and the green decreases towards 0. So I get the ratio is what? The ratio is, this is still positive 0. So the ratio is like 1 divided by 0 plus, which is plus infinity. Do you see 1 over 0? If you write 1 over 0 plus, you see that it approaches, algebraically, you see it approaches to infinity. Do you agree? Numerator gets to 1, denominator gets to be smaller and smaller number. You can actually see that this is happening geometrically, guys, right? So let's see that this is happening geometrically. This is already too large for me to draw here. So I will just make a much smaller angle. Look at it, guys. Suppose I just select this is my my angle. All right, so this is my, I extend theta to be this, and this is my let's call this phi. This is my phi. Now, how do I draw it very well? Look at it. I just take this curve and I extend it, and I simply just extend the radius. You see that? I extend the radius, and now what do I get? This part is my tangent of phi. Do you understand why that's tangent of phi, guys? So what's my intuition is that I want to divide by 1. It's opposite divided by 1 that gives me tangent. Are you clear? So what I do is, you see this this red and green, this new triangle that I drew. This is red and this is green, and I just made that triangle larger until the adjacent side, until the horizontal side of the triangle is one unit length. You see, I just scale it up, and as I scale it up, I see that the opposite side now is much longer than before, and as I increase the angle, the opposite side will go to infinity. Clear? Wonderful. Let's clear it. Now, please tell me what is what's going to be the limit if I do it in the other direction. So what's the limit as I take theta and approach pi over 2 plus of tangent theta? Do you see where pi over 2 plus is, guys? It means that this is pi over 2 and I'm slightly above pi over 2. So that means that I'm moving in this direction towards this edge. What's going to be that limit, please? Well, the limit is telling you, Sophia, where we're going, right? We are approaching pi over 2 plus, which means in which quadrant am I approaching? And what are we approaching? Okay, one person has it. Elazar, sign is also important. So y minus, yes? We are approaching minus infinity. Could anybody tell me why minus? Oh, you see it. Because let's approach anywhere, guys. Let's go anywhere here, right? If you take this segment, then this rope is positive, but this part it's getting smaller, but it's negative, right? So the ratio of tangent is always negative. So what do we get for tangent here? We simply get roughly 1. I don't care if it's 1 plus or 1 minus, it's really 1 minus, but it's really a number that's getting bigger. Numerator is getting bigger, denominator is approaching 0 minus, and that's minus infinity, right? I can see that geometrically, guys, you understand? I mean, instead of actually using numbers, you can think of them much better geometrically by seeing what happens to the triangle. It's pretty, division and multiplication was done before you assigned fractions. Before, the fractions is like labeling or assigning codes. You could multiply and divide without explicitly knowing what's the value, what's the numeric value, you understand? That's the interesting thing about it. You could actually take the square root of a number without knowing what the number is. Good. So we understand tangent. Would you like to tell me here, guys? Let's see, what can we do here? How would you see in this picture? How would you see maybe? Maybe we'll do something like this. Here is a circle. Okay, here is a circle, and here is one axis. Here is another axis, guys. And here I'm drawing drawing the angle. The angle, you know, many of you draw the angle here, but that's truly the angle is here. That's the theta in radians, you understand? It's the crust of the pizza. Now, in this picture, can you draw the picture? I'm not sure if you can answer it, but do you see where, I can always imagine that this is 1. Where in this picture do I see secant? Secant is 1 over cosine, right? Or it's the hypotenuse divided by adjacent. So where is secant in this picture? So you see you have, this is my sine. This is my cosine. So this is cosine theta. This is sine theta. Where in this picture is, this is all 1, you can just remember it, right? In this picture is secant. Remember what you do, guys. It's very one simple advice. Just maybe you can try to describe what I do. You remember when you do secant, you take you divide by something. Yes, secant is 1 over cosine, correct? Or it's the hypotenuse divided by adjacent. Now, why isn't it easy to divide by the adjacent? If you can answer that, you can figure out how to draw secant in this representation. Yeah, so it's 1 over cosine. Now, what's so bad about dividing by cosine in general, in a general position? Sometimes it's not hard to divide by cosine, but sometimes it is. Most of the time it is. Now, why is it difficult to divide by cosine? Well, if it's 0, then it's undefined. But why is it in general difficult to divide by cosine, guys? Because cosine is generally not what? Not 1. If you understand that, guys, then you understand what you have to do, correct? You want to divide by 1. Good? Yes, the sine isn't 1 either. If I have to divide by sine, I mean, you can do that. Or you can visualize on the unit circle all the trig functions very easily if you just consider that very simple problem is that you are not happy when you have to divide. If the hypotenuse is 1, that's why sine is easy to kind of calculate. Your sine, you see this hypotenuse is 1, so you see the sine here. So whatever you divide by, you want to make it 1. Do you understand? So how do I, if I want to calculate secant, look at it. If I want to calculate secant of theta, I am going to divide, it's the same as 1 over cosine theta, which I don't like. So what am I going to do? I'm going to make this 1 because I want to divide by 1. Do you agree? Same as with the tangent. So I'm going to divide, I'm going to extend this, and I'm going to extend here. And here, guys, look at it now. This is two similar triangles. Do you see the dotted large triangle and the triangle with the green and the red segments? It's the same. It's a proportional triangle. Do you see that? So tell me, in terms of this new triangle, where do I look to see secant? I look to what? Where a secant is, remember, it's hypotenuse divided by adjacent. It's kind of, the answer is obvious. Where do I look to see the secant now? Well, outside the circle is too vague. What do I look at? Exactly, hypotenuse. I look at hypotenuse, guys. Do you see? Do you understand? I hope it's very simple, guys. You see how it's in my mind. I do not bother with some stupid mnemonics and whatnot. I just think, okay, what's the idea? And the idea is that cosine is adjacent over hypotenuse. So if the hypotenuse is measured as 1, it's very easy to divide by hypotenuse. But if I do secant, it's hypotenuse over adjacent. Now adjacent is usually not 1, so I make it 1. I just scale the triangle. Do you understand? Scaling the triangle, I preserve similarity. Do you agree? Symmetry is preserved. So do you follow me, guys? It's something divided by 1, right? So if I have to divide this by 1, I make sure this is of length 1. And so what do I see here? I would color it in orange. This is secant theta. Yes? This is secant theta. Can you tell me what will happen to this orange line if I push a limit as theta goes to 0? I mean, it's pretty obvious, right? What happens, first of all, if I take limit where theta approaches 0 of secant theta, I get what? Exactly, you get 1. You see that basically this orange line will get, it merges. You see the orange line will follow this dot and it will merge to this location. It will merge to the location 1, right? So it's 1. Now tell me more interestingly, what's limit as theta goes to pi over 2 with a negative of secant theta? That's what? You began disappearing, guys. You avert my gaze. Why is that? Am I not pretty today? You're showing your disgust and you don't want me to see it? Ilyasu, you disappeared. Sandra, maybe I've seen you before. Enrique, I don't remember what you look like. Right? So, secant of theta is what? Oh, here we go. Great. Ilyasu, Sandra, welcome back, right? Good. I'm still alive. I'm still here. Good. So what is secant? Infinity. Do you all see why it's infinity, guys? Look at it. What happens if I rotate closer to pi over 2? If I rotate closer to pi over 2, secant, this orange line, has to meet that dotted perpendicular line emanating from 1. Do you understand why? Because I'm always going to normalize or change the scale of my triangle, so I divide by 1. Do you agree? Which means what? Which means that I can easily see the graph of all of the secant if I just follow this dotted line, right? So if I rotate a bit more, this is my secant. If I rotate more, it will take longer to meet the dotted line. Do you all see that? You can of course do. You might say, oh, I can do it arithmetically. I can see that cosine approaches 0. And when I approach pi over 2, so I divide hypotenuse, which is 1, by something close to 0, and that will be infinity. Grant, infinity bothers you, huh? Yes, it bothers me also. I mean, I've heard this Friday, I heard eulogy, and this guy was saying, can you comprehend the infinite? Can you understand what is infinity? And I thought, yes. But this guy was whatever speaking. Of course you can. It's Cantor's theory of the infinite. Of course you can comprehend it. It depends, of course, what you mean by comprehend. Good. Understood? So you see why this limit is infinity as I approach this way. If I were to go in the opposite direction, and of course I stretch the green line to -1. You see, if I, of course I jump, guys. You see, if I want to calculate secant in the second quadrant, I will use this dotted line. I will stretch instead to -1, right? So if, for example, I have to calculate secant over here. What I do, I will extend the adjacent to be at this point, and I will extend this thing look here, right? So the length is still going to be infinity, but you remember, because it's over negative axis, you remember that you report it as minus infinity. Good? Very easy. Agree, guys? I mean, you see, if you understand that you don't like to divide by anything other than 1, then you understand why you will do this thing, right? And maybe for you it's harder, it's because you're good at multiplying and division. I mean, I'm terrible at it, so I had to think this way. Good. So what's happening here? Now help me please, guys, with this new task. You are going to tell me where I have to look to find cotangent. Will you help me do that? Right, we found, you know what's cotangent. We found tangent, we found secant. Let's think about cotangent. You remember those names, right? I'm kind of loose about it, but you remember that's very simple. Just
Yes.
yes, I hope you do. Okay, so here it is, and here is my drawing over here, and we will try to find, let's say we'll take this angle. That's sine over cosine is tangent, Elazar. So this is, if this is my angle, let's just draw it carefully, guys. If this is my angle theta, then the green part is cosine theta, and the red part is sine theta, okay? And I assume that the radius is always measured in radius units, so it's 1. Moshe, you did what to get the same answer to what? I'm sorry. Same answer as what? Okay, guys, so my question is on the graph, as I'm waiting for Moshe's reply. I'm interested if you could tell me where I look to find the picture, to see geometrically where I see cotangent. Cotangent theta. Yes, where is cotangent theta in this scheme? Moshe, I do not know what problem you mentioned. What's okay for what exam? Okay, guys, where do I see cotangent here? Now, Moshe, I just saw your message to me, and you said something, you did something on Maple and you get the same answer. I have no idea what you did on Maple and what answer did you obtain. So that was it. Okay, but we'll go there, right? So good. So what I'm asking, guys, is here is cotangent. So yes, you all see why we extend the triangle. What is cotangent? Cotangent, very simply, is one is the radius. No, sorry, not 1, right? Cotangent is cosine theta divided by sine theta, right? And specifically, we can see cosine here. What we're not happy about is that we have to divide by sine, which is usually not 1. Do you agree? We don't want to divide by sine. So where do we see cotangent? Look at it, guys. It's a bit, let's see if I can, you know, sometimes you scale it up. So sine, this thing that I divide by, I want it to be of length 1. And the easiest thing to do here, perhaps, is to draw a dotted line over here. Why do I do that? Is because you see, guys, that if I extend this segment, if I extend sine, I will extend sine to be of length 1. Now sine is of length 1. And now what is my, if I extended sine and that's length 1, what's the what sort of triangle do I get? Okay, sine has to be extended to be of length 1. For that to happen, I can scale this triangle. I can scale this triangle, pushing it, you know, it's kind of actually rather far. So I push it over here. Here it is. I push that triangle, and that makes this red segment that makes that red segment equal to 1. You see the segment is now of length 1. And the segment that, where do I see in this picture, where do I see cotangent? Well, it's right over here, for instance, right? Because this divided by that, so it's this is cotangent, theta. Good? You can draw it in some other place if you prefer. Good? You understand what I do, guys? In essence, I just take this triangle and I extend it, this triangle, until this length is 1. All I do is extend until this length is 1. Here it is. And then that will extend the horizontal segment. And then that orange part is the extended horizontal segment. It's now cotangent. Clear? Easy, right? Just, yeah, so good. So we have some notion of trig functions. It's exciting, I hope. Now let's try to understand some important questions, which maybe will be important on your extra credit. Is sine and cosine polynomials? Right? Do you first, before answering yes or no, do you understand what I'm asking? Right? I'm not saying we have to decide whether they are or not right now. Are they polynomials? What am I asking? Well, let's try to figure out. What am I asking? When I ask whether or not you're a quadruped, right? You all understand what that means. It means, do you walk on fours, right? Do you walk on all fours? If so, then you're a quadruped. So then similarly, do you understand what am I asking when I think whether or not sine is a polynomial? They can be represented not as rational numbers, Grant, no. Can I create a process, right? So what I'm asking is something that you have to kind of grasp, guys. Can I create a process to calculate sine, right? So for instance, sine of theta, what is done to theta? That's the question that you always ask yourself. How is sine digesting? What's the method of digestion, right? So when you say sine of theta, some people imagine that what I said is something, and you will see mistake like it's like sinus, it's the sin multiplied by theta, right? So never make such a sin to imagine this is what it is, right? It's it just is just an expression. It's a name of a function. It's like saying Arkady of theta. And what is that? Right? What is Arkady doing to theta? How is Arkady digesting theta? Good. That's what sin of theta is. And then the question is, can I simulate this digestion by multiplication and addition? So for instance, how is sine of pi over 7 to be calculated? Is it maybe something like 1 minus pi over 7 cubed plus pi over 7 to the power of 5 times 12 or something, right? Could that be the formula that calculates? In other words, could sine of theta maybe it'd be this formula: 1 minus theta cubed plus 12 theta to the power of 5. You understand? I'm just creating a polynomial out of the blue. I'm not saying that's this one, but can I create a digestion mechanism that will tell me what sine is doing to the angle? How is it explicitly churning its ratio out of the angle? Right now, we just take the measurement. We know that sine of pi is 0 just because we see it, just because we see that the arrow of my clock is lying on the negative x-axis and sine is not is 0. You understand? So the question, guys, has to be very significant to you, very obvious to you. How do I calculate? That's first question. We will address it later. Next is, of course, some important properties for trig functions. Guys, so we ask whether or not sine and cosine are odd or even functions. So the name odd and even, let me just remind you what is that. So a function is even if it has this property. Okay, if it does not care whether you feed it the input or negative of the input. And it has this type of symmetry. You see, if you take the positive x-axis or you take the negative x-axis, the function digests them equally. You understand what that means? I'm not saying minus x is necessarily negative. I'm just saying that give a number or the negative of the number and the function doesn't care. It will give you the same result, right? That's called even. It doesn't matter why. I mean, we can discuss what's the analogy, but then we have also odd. Would you remind me what is odd? So if you give negative of the input, you get what? Exactly. Exactly. So then you get minus f of x, and then you have this type of symmetry. If you draw the graph, it's this and this. Okay. So it basically, if this is the input f, then it will just take the same thing and create minus f. Good? Brilliant. Good. So now, why is it obvious that sine is an odd function? Look at it, guys. Here I open to an angle theta and simultaneously to an angle minus theta. Do you see that? I get the rope above the x-axis and the rope below the x-axis. They're of the same length, but one is negative, one is positive. Whereas if I do that for cosine, you can see cosine remains the same segment. And you can open it to any angle. It could be a small angle or it could be a large angle. Maybe if the angle is large, it will be over the negative x-axis. The point is theta or minus theta produce the same x component, but different y components, which makes opposite y components, which makes sine an odd function and cosine an even function. Do you understand? Can you see it, guys? All right. So it's going to be, all those properties will be important for us. We will utilize many properties. Now, this is something that I'm not sure, it took me a while to explain in the morning. I'm hoping it's not going to be the situation, guys. Let me just see for a moment, guys. So imagine that a radius of wheel is, 1/4 meter. Okay, the radius of the wheel is 1/4 meter. The wheel made 1 revolution. What distance did you travel? Exactly. Pi also, so how much did we will travel? So 1 full revolution, it means 2 pi multiplied by 1/4, which does what? Which means that the distance traveled is pi over 2 meters. So a little bit over a meter, because pi is 3.1 something, right? A little bit over a meter. Do you see why did I multiply by 1/4, guys? Do you understand that? It's like, for instance, if I had 1,000 meters, how would you convert it to kilometers? Right? 1,000 meters, you convert it to 1 kilometer, right? So then if you have 50 meters, how many kilometers is 50 meters? What do you do? Right? When you have 50 meters, how many kilometers are there? That's very obvious, I hope. Right? So somehow, either because of the way I was explaining it, or maybe obviously something before, it was somehow strange to people. What do I do, guys? And not even the answer. I want you to understand truly what's happening here. So what you do is you take 50 and divide by 1,000 and then multiply by 1,000 meters. You see, because this part, guys, this part, I mean, I can say this is still equal. This is still equal. And I prefer to use triple bar to indicate conversion. 1,000 meters are converted to 1 kilometer. Do you see? So this is 50 divided by 1,000 kilometers. Do you understand what I did? The conversion, because 1 kilometer, it's like, I imagine a bus, right? 1 kilometer is a bus that takes one, or a train that takes 1,000 passengers. 1,000 meters as its passengers. Good? It's that what I personally imagine. I mean, I think you should understand such analogies. So, where was I? Yeah, so here, guys, we need to figure out the conversion of radian measure to figuring out x and y. So usually the circle that I draw, the x and y, are not on the unit circle. By that, all I mean when I say not on the unit circle is that the radius of the circle that I created is not measured. The scale on the x and y axis does not correspond to the scale on the radius. You understand? If the radius is exactly the size of the scale on the x-axis or the scale on the y-axis, then we call it a unit circle, but otherwise it's not. So in general, a radius has r scales of x-axis or r scales of y-axis. You'll see radius is r. Now, theta is in radius units. So theta, let's say if I say theta equals to 2, guys, 2 radians. 2 radians means 2 radius lengths. 2 radians is 1 diameter. Good? The arc is of 1 diameter. And if I want to convert it to, let's say, centimeters, let's say r measures, the radius measures r centimeters. That means that the arc will measure 2 times r. Right? 2 radians carry out together r centimeters each, so it's 2r is the length of that circumference. Clear? That's r theta. Now, how do I convert x and y? So I can say that cosine is equal to x divided by the length of the radius, and that's cosine. And y is equal, and y over r, y divided by the radius will be sine, opposite over hypotenuse. And that allows me to very easily convert. Look at it, because I just multiply by r, and I see that the coordinates x and y are simply r cosine, r sine. It's going to be important. I need to be sure that you understand it. I have a small question, guys. Let's see if you comprehend it. Why did I divide by r? So why do when I define sine, or at least how you heard it in high school, why do you say opposite divided by hypotenuse? What is that division supposed to achieve? Quick question, when is the test? Yes, that's good. The test will be when we finish trigonometry, which makes me unable to answer your question because I have no idea when we finish trigonometry, because trigonometry was supposed to be something we all know, but we do not. Right? So guys, what do you want from me? It's like you're asking me, when will you grow arms and legs? I don't know. When you decide to. When will you learn to speak? When will you learn to walk? I don't know. It's when you decide to. My goal is not just to give you tests. I don't care about it. Honestly, I hate tests. My personal goal is to teach you the subject. Good? Yes, Elazar, if you love tests, I'll give you 70 problems just for you. All right, back to my question. We were almost done. I see you're already ready to escape. One last question before you escape. Why do I divide by the hypotenuse? What am I trying to achieve when I divide by the hypotenuse? Yes, okay, Sophia, I think you have the right idea, but I need it phrased very easily. Well, Grant, yes, I suppose you're right, but what I'm doing is rescaling. I am rescaling this. I'm just reporting this information in terms of, it's like if you're told don't report it in meters, you have to report it in kilometers. Do you understand? So you have to report the length of the opposite side in radius units. If the hypotenuse is your radius. If it's not reported in radius units, then you have to convert. Do you understand? If the hypotenuse is 5, the reason you divide by 5 is because you convert it to the size of the radius. Okay? Do you see that? It's very simply a matter of how you report this information. So I just have a standard way of telling you what's the length of the rope. I always mention it as a percentile of the length of the radius. Okay, at that point, I already see some of you are escaping. That's why I find the ratio. So if you want to escape, guys, I wish you adieu. If you want to, I'll show you somewhat when we're question or answer some questions that you have as you were, of course, studying very hard and trying to understand this material. Yes, I'm sure that when the class is over, you just are so excited and you continue solving problems from the book like I suggested. Because that's the way you get to know this material. Final exam, guys, let me tell you, right? So don't worry so much about my in-class exams. They're not in class, they're actually take home. The final exam is timed. It's on what do you call it? On my open math. And it's conceptual. Last semester it was, and it will also be conceptual to prevent cheating, which means you need to not just solve questions, but really understand the idea behind solving it, right? The abstract idea. But fortunately, that's all I do. I just only ask abstract questions. Conceptual means philosophical, precisely, right? So I love philosophical questions personally. So why do I personally care about sine and cosine? Because I have a susceptibility to philosophy. That's how I came to this, in fact. Right? It's a silly subject, but somehow always, always gets to me. I like things, I like paradoxes. That's my thing. Yes, Asror, that's my email. Okay, and if you're leaving, guys, then goodbye. Hope you enjoyed the class. Hope it is making you happier rather than sadder.